Namaskar. So yesterday we discussed what is queuing theory, what is waiting line theory. We discussed some introductory part of queuing models, also elements or components of queuing systems. So today we will discuss the next part of queuing models. So queues, or it is also called as waiting line, affect people every day. A primary goal is to find the best level of service, and analytical modeling can be used for many queues. So for more complex situations, computer simulation is needed. So we'll discuss queuing system cost. So cost of providing service and cost of not providing service. So if we are not providing service, then waiting line is there, and more waiting, so there is a loss of orders, or customer is not satisfied with your service, so that is a loss. Okay, so here in this diagram you can see the three curves. One is downward curve, that is cost of waiting time. Cost of waiting time reduces as service level increases. Then cost of service providing increases as service level increases. Yesterday we discussed the same graph, and with the help of these two curves, so total expected cost we can find out by considering optimum level service. So the center line is optimal service level, where the cost of waiting time is also minimum and cost of service providing is also minimum. So this is a intersection point which is optimal service level. So you can choose this for any queuing systems. So already we discussed yesterday what is cost of providing service and what is waiting line cost. So today we'll move to one example. So there are let us see one example. This example is called as 3 reverse shipping example. Here in this problem there is not 3, but it is a one type of example. Let us have one question. Read this question carefully. Note down this question carefully. So average of 5 ships. 5 ships are there. Arrive per 12 hours shift. Per 12 hours shift, 5 ships arrives. A team of stewardess unload each ship. Each team of stewardess cost rupees 6,000 per shift. Per ship their cost is 6,000 rupees. 12 hours shifts means in per daily there are 2 shifts. So per shift the cost is 6,000 rupees. The cost of keeping a ship waiting is 10,000 per hour. Cost of ship waiting is 10,000 rupees per hour. Now, how many team of stewardess to employ to minimize system cost? So this is your question. Here a number of team stewardess. Suppose, see, cost of one stewardess cost is 6,000 rupees. 6,000 rupees. So 6,000 rupees is there. 6,000 rupees. So if one stewardess is there, the cost for one shift is 6,000 rupees. And so cost of keeping a ship waiting is 10,000 rupees per hour. So here, just wait. Here there is a printing mistake. You take here 5 hours, 5,000 rupees. 5,000 rupees. You consider 5,000 rupees per hour. This cost is 5,000 rupees. Here, if one steward is there, so average hours waiting per shift is 7 hours. Average hours waiting per shift is 7 hours. So 7 into 5, 35,000 rupees. 35,000 rupees. If two stewards are there, average waiting per shift is 4. Average 4. So 4 into 5 is 20,000 rupees. Also 2 stewards cost is 12,000 rupees. If 3 stewards are there, number of team of stewards is 3. Then average hours waiting per ship is 3. And 3 5s are 15,000 rupees. And 3 6s are 18,000 rupees. Similarly, if number of team of stewards is 4, then average hours waiting per ship is 2. So 2 into 5, 10,000 rupees. And 4 into 6, 24,000. Now you just add this. So 10,000 plus 24, that is 34,000. 15 plus 18, 33,000. 20 plus 12, 32,000. If you see the total cost, so if one steward is there, 41,000. If 2, 32,000. If 3, 33,000. And 4 stewards, 34,000. So this is a minimum cost required. So you can choose 2 stewards and 4 hours waiting per ship. Okay, in this way you can solve this queuing problem by minimizing cost. Here there is a printing mistake. Here you have to consider 5,000 per hour cost of keeping ship waiting. Okay, the queuing system is determined by arrival characteristics, queue characteristics, and service facility characteristics. The size of arrival population, either it is infinite or limited. Then arrival distribution is also important. You have to consider either it is fixed or random, either measured by time between consecutive arrivals or arrival rate. The Poisson's distribution is often used for random arrivals. So arrival characteristics are very important. Then Poisson distribution is a average arrival rate. Average arrival rate is known. So average arrival rate is constant for some number of time periods. Number of arrivals in each time period is independent. As the time interval approaches 0, the average number of arrival approaches 0. So let us discuss this Poisson's distribution. Here lambda is the average arrival rate per time unit. Here P of x, Px, the probability of exactly x arrival occurring during one time period. So it gives, it is shown in screen, on a screen. So Px equal to e raised to minus lambda, then lambda raised to x, and then exponential of x. So we have to consider behavior of arrivals. So most queuing formulas assume that all arrivals stay until service is completed. So barking refers to customers who do not join the queue, and reneging refers to customers who join the queue but give up a leave before completing services. Okay, so we'll see one by one. Queue length. So it is a maximum possible queue length, either limited or unlimited. Then service discipline, use FIFO, that is first in, first out. Service facility characteristics, configuration of service facilities, number of servers, that is channels, number of phases, that is service stops. Then service distribution, the time is the time it takes to serve one arrival can be fixed or random, and exponential distribution is often used for service distribution. Already we discussed. Then exponential distribution. So mu is the average service time, t is the length of service time, and probability that service time will be greater than t, that is pt, where pt is e raised to mu t. So measuring Q performance, so rho equal to utilization factor, that is probability of all servers being busy. Then LQ is the average number of queues, L is the average number in the system, WQ is the average waiting time, and W is the average time in the system. So PO is the probability of 0 customers in the system, Pn is the probability of exactly n customers in the system. And Kendall's notation. Here, Kendall's notation, that is A slash B slash C, ABC. So here arrival distribution. So arrival distribution, M for Poisson's, D for deterministic, and G for general. So B for departure distribution, C for number of parallel service in channel in the system. Now B is for service time distribution. So M for exponential, D for deterministic, and G for general. So S is the number of services. So these are Kendall's notation. So D.G. Kendall in 1953 and later on the A. Lee in 1966 introduced useful notation for queuing models. This is one of the notation. So the queuing model covered here all assume arrival follow Poisson's distribution, Fi FO serves, single phase, unlimited queue length, steady state condition. So we will look at 5 of most commonly used queuing systems. So first, name of Kendall notation. So this is notations MM1, M/M/1. This is simple system. MM1. So MM1 is a customer service desk. Customer service desk in a store. So this model is symbolic represented by MM1, that is FCFS infinity. That is first come, first serve, and second is this represents Poisson's arrival, Poisson's departure, single server, first come, first serve discipline, infinite population. Since the Poisson's and exponential distributions are related to each other, both of them are noted by symbol M due to Markovan property of exponential distribution. The second line, multiple server M/M/S. So it is an example of airline ticket counter. So though this model is also represented by M/M/S, here it is generally queuing model in which arrival or service rates depends upon the length of queue. Some persons desiring service may not join the queue since it is too long, thus affecting the arrival rate. Similarly, service rate is also affected by length of queue. Then constant service, that is MD1. So this is a mixed queuing model. MD1 is a mixed queuing model. So in this mixed queuing model, so this model represents arrival rate is, so this is used for automated car wash. Here arrival rate is Poisson's distribution while service rate is deterministic or constant. So similarly, MM/S infinity and n. So an operation only with only 12 machines that might break. Okay, so there are these different types of candles notations. Usually these notations are classified based on probabilistic queuing models, deterministic queuing models, and mixed queuing models. So probabilistic queuing models are total 10 types of probabilistic queuing models. Then deterministic queuing model is one, and mixed queuing model. In this way there are 12 models. The single server queuing system. So a single channel queuing problem results from random interval time and random service time at a single service station. The random arrival time can be described mathematically by a probability distribution. The most common distribution found in queuing problem is Poisson's distribution. The most common distribution found in queuing problem is Poisson's distribution. So this is used in a single channel queuing problem for random arrival where the service time is exponentially distributed. The section ahead. So here Poisson's arrival population is unlimited. Then all arrivals wait to be served. So lambda is a constant. So mu is greater than lambda. So average service rate is greater than average arrival rate. So operating characteristics of MM1Q. MM1Q is a model 1, probabilistic model 1, MM1. So average server utilization, average server utilization equal to lambda by mu. Here what is lambda? It is average arrival rate and average service rate. Average arrival rate divided by average service rate. Then average number of customers waiting equal to average arrival rate square divided by, in bracket, average service rate minus average arrival rate into average service rate, that is lambda square divided by mu minus lambda bracket complete multiplied with mu. Then average numbers in a system, that is L equal to LQ plus rho. That is the average numbers in a system. So average waiting time. So WQ equal to LQ equal to lambda divided by mu in minus mu minus lambda. So average time in a system, that is W equal to WQ plus 1 by mu. Then probability of 0 customers in a system, that is PO equal to 1 minus lambda by mu. And probability of exactly n customers in a system, that is Pn equal to lambda by mu raised to n into PO. So this is about Kendall's notation. So using this Kendall's notation, you can solve the problem. You can use these notations to solve different types of problems. Okay. Then Arnold's muffler shop example. We'll see one more example. So in next lecture we'll see this example. So let us total cost of queuing system. So how it is calculated? Total cost equal to cost of customer waiting time per period into average number of customers in the system plus cost of services per time period into number of services. Okay, so this is very important formula. Total cost equal to cost of customer waiting time per time period into average number of customers in the system. So per customer and average of waiting time. Then cost of services per time period and number of services provided. So in this way, this is the total cost of queuing system. Then let us discuss multiple server systems. in multiple server systems, so we have to consider Poisson arrival, exponential services. In previous section we discussed the single service center. This is single server queuing system. Now we'll discuss multiple service server systems. So Poisson's arrival, exponential service time, then S services, then total service rate must be exceed arrival rate. So S mu greater than lambda. So many of operating characteristics formulas are more complicated. Okay. Then single server with constant service time, that is MD1. Here in this case the Poisson arrivals, constant service times and has shorter queues than MM1 system, that is LQ and WQ are one half as large. Okay. Then single server system with general service time MG1. So here Poisson arrival general service time distribution with known mean, that is mu, and standard deviation. So this is what difference. So this is a mixed one. Then multi-server systems with finite population. So this is also one of the system, that is Poisson's arrival is considered. Then exponential service times are there. Then S servers with identical service time distribution and limited population of size n, and arrival rate decreases as queue length decreases. So more complex queuing systems are there. When queuing system is more complex, formula may not be available. The only opinion may be use computer simulation, which we will study if time permits. So with the help of computer simulation you can solve the complex problems also. For simple problems you can use these Kindle's notations and these formulas. Okay, next part with few examples we'll see in a next session. Okay, if any doubt you can ask in a comment box or you can ask in our doubt clarification sessions. We'll see few more problems and examples on this different conditions of queuing systems in next lecture. Thank you very much.